Hello everyone, Assalamu alaikum. I am Muhammad Mahinur Rahman from Bangladesh University of Engineering and Technology. I will be presenting you our paper Design and Performance Assessment of a Locally Developed Solar Pipe Light. Our work is partially funded by GIZ. The whole presentation is divided into 6 different parts: the objectives, design and construction, experimental test setup, field implementation, results and analysis, and finally conclusion. Moving on to the objectives of our work. The first objective is that we have tried to showcase an alternative to artificial lighting. We have emphasized on energy saving for improved environmental conditions and a sustainable way of living. We have tried to utilize sunlight into a building for interior illumination. Our design is primarily focused for workplaces. And we have designed, constructed, implemented and tested a solar pipe light, and the results from the solar pipe light are promising and proves that the design has enough potential to lessen the future energy crisis in Bangladesh. These are the 5 objectives, and now we move on to the design and construction of our solar pipe light. The solar pipe light mainly has 3 parts: the top part, the reflective tube, and the diffuser. The light passes onto the transparent top part from the surroundings and then moves into the reflecting tube, where it gets reflected multiple times and then passes into the diffuser, where it is refracted and scattered into the building interior. The efficiency of the design depends upon the geometrical factors such as the length of the tube, the diameter of the tube, the number of bends and their angles, and the type of diffuser used. Figure 1, we present the exploded view of the solar pipe light. In figure 2, we show the top view of the solar pipe light. And the exploded view clearly shows the transparent top part, the shiny reflective tube, and the diffuser part. For the construction, a local market survey was carried out, where we have chosen cost-effective materials that are easily available in Bangladesh. And for the top part surface, we used clear acrylic plastic board. For the reflective tube, we used a nickel-coated galvanized plain sheet, disregarding aluminium due to being less shiny. And for the diffuser, we have used prism plastic boards. Moving to the experimental test setup, the constructed design was set up for an experiment in the darkroom of the Department of EEE BUET, where we also designed a steel structure to support the solar pipe light, to support the light source. Since it's inside a laboratory, we used artificial lighting, and the 2 types of artificial lights were used to simulate 2 different illuminations of 2 different weather conditions: the sunny sky, which is simulated by an 80-watt LED street light, the clear cloudy sky, which is simulated by a 20-watt floodlight. Both the lights were hosted over the structure, and we have also used black curtains to wrap up the solar pipe light so that the light from the inside does not come out of and cause errors. And the distances from the light source to the top surface of the solar pipe light was 18 inches, and from the diffuser surface of the solar pipe light to the ground was 45 inches. This is more clearly shown in figure 3b, where we see the schematic of the structure designed, and illuminance readings was taken at 3 different surfaces: the top surface, the diffuser level, and the ground level. The data was taken by using an HTC LX101 luxmeter, and in the measurement orientation shown in figure 4, the circular surface is divided into 4 different parts. For each of the light, 4 different readings were taken. Natural light was not completely substituted, but it served our purpose, which is an assumption for our experimental test. Now, moving into the field implementation, our constructed solar pipe light was implemented at Rimso Foundation Battery Manufacturing Factory at Narayanganj, where the roof was cut into appropriate diameter and the solar pipe light was placed into it. The vertical distance from the solar pipe light diffuser surface to the ground is 13 feet. And for measurement of the performance of the solar pipe light, here we have used LDRS LDRs at two different levels, the diffuser surface level and at working level. The working level is actually 8 feet below the diffuser surface level. The LDRs were connected to market available data logging devices, which is connected to the internet for remote monitoring. This slide shows the implementation of the solar pipeline in factory. Before solar pipeline installation, we see that artificial lights were used, and after solar pipeline installation, artificial light needs not to be used. Rather, the light provided by the solar pipeline is illuminating the room rather than using artificial lights. And figure 8 and 9 shows the installation at the roof, how the roof is cut and the solar pipeline placed. Now moving on to the results and analysis section. In our results and analysis, we have used three different horizontal illumination based metrics: the daylight factor, the minimum daylight autonomy, and the useful daylight illuminance. The daylight factor is actually the ratio of the indoor illumination to the outdoor illumination. It's expressed in percentage. The minimum daylight autonomy is the percentage of annual daytime hours when the illumination at the measurement point is above a specified illumination level, and the useful daylight illuminance is the range of illuminance values considered useful. And there are different standards that we have followed for the measurements for analysis of the data. According to Illuminating Engineering Society, we see that the range of illuminance acceptable is 600 lux to 900 lux, but for Bangladesh National Building Code it's 300 to 1500 lux, and for Illuminating Engineering Society of North America it's 300 to 1000 lux. And for the daylight factor, we have considered an acceptable value of above 2%. Above 5% is considered as a well lit room. And now the laboratory test results. The maximum illuminance that we have achieved using our light meter and from the light source is 110,000 lux for the 80 watt light and 30,000 lux for the 20 watt light, and they very well simulated, as we have stated earlier, the direct sunlight condition and the clear cloudy sky conditions. In Table 1, we can see the results that we have obtained from the laboratory test. For the 20 watt and for the 80 watt, 4 sets of readings were taken as the measurement orientation in figure 4. And for both the cases, the average daylight factor is above 4%, which is very acceptable and proves the viability of the design. And the average daylight factor is calculated by calculating the daylight factor at each of the points and then averaging them. And the minimum daylight autonomy and useful daylight illuminance measurements were not carried out, since since the whole experiment is carried out inside a laboratory under artificial lightings. And moving on to the field test analysis, figure 11 shows the plot of the data from the LDRs, the light dependent resistors, and the two different light dependent resistors placed at two different places, the workplace and the diffuser. We see that the pattern of data incoming of the light lux illuminance is very close. For our field test analysis, we have chosen data from two different days, from day 1 where it was clear day with little clouds, and from day 2 which was a cloudy day. And the data of analysis was for 12 hours, from 6 a.m. to 6 p.m. when sunlight is usually available. And for those 12 hours, we have taken 720 samples of data at 1 minute intervals. The daylight factor, minimum daylight autonomy, and useful daylight illuminance found from the field test is shown in table 2. We can see that the daylight factor for day 1, which is a sunny day, is good. It's above 2. And for day 2, the daylight factor is below 2, but day 2 has a higher minimum daylight autonomy percentage and a higher useful daylight illuminance percentage. The lower daylight factor may be because of the diffused light from the clouds. So the field test proves the viability of the design. Also, to analyze the spectrum of the light from the solar pipeline, we have used an spectroflickerometer where we observed the light spectrum from the solar pipeline as seen in figure 12, and also the light spectrum from the compact fluorescent lamp. It is seen that the light spectrum from the solar pipeline matches completely with the natural sunlight spectrum shown in figure 13. The spectrum is very similar to the sun. Now moving into the conclusion. So in our paper we have designed, constructed, implemented and tested an inexpensive solar pipeline. We have implemented that in an industry premise and tested under 2 different weather conditions. The performance was assessed using 3 different metrics: daylight factor, minimum daylight autonomy and useful daylight illuminance. Both the assessments at the laboratory and the field test shows promising results, and thus the solar pipeline is an easy solution for harnessing daylight as an alternative to artificial lighting, and in the context of Bangladesh the solution is sustainable and has enough potential to lessen the future energy crisis. We, the authors, would like to acknowledge the Department of EEE BUET and BUET Energy Club for providing necessary support for experimentation, RIMSO Foundation for supporting in field implementation, and GIZ and Sustainable Renewable Energy Development Authority for patronage and funding support. Thank you very much. If you have any questions, please let me know.